first I'd like to thank the organizers for organizing this wonderful workshop and for inviting me. And well, I'm actually not a transparency person. I'm more a blackboard person, but I use transparencies to make the obvious mistake to put too much information in there. So don't read everything I'm going to present here. So in the morning in Odette's talk, we have already seen what the Loewner equation is, and we have seen over the last few years actually that the process SLE2 is an important process, SLE4, SLE6, SLE8. So I won't speak about these different models that are conjectured in the scaling limit to be represented by SLE. I would just focus on SLE, explain briefly again what it is, and then just look at basic properties of SLE. So I won't talk about the physical or probabilistic models behind it, actually. So let me first recall, well, the Loewner equation. So that already explained it. So you can easily just view it as a very simple ODE. So the ODE is z is a point in the upper half plane, and then it's just z dot is 2 over z minus xi, where xi is just a real valued continuous function. So xi is a function from the real to the real line. Typically t is time, so t should be positive here. And then this, well, you just solve the ODE. It turns out, so if you start with a point z in the upper half plane and you let the equation run, then this point will move downwards. And this is basically the phase diagram. So if the singularity xi sits over here, then at that time, points directly above it will flow straight down, and points to the side will just move to the side. This is basically the picture. Then you can look at the time t map of that flow. Yeah, so now you start with a point z, let it flow for time t, so you get the point gt of z, which is just z at time t. And then you can ask yourself, well, for what times does it actually exist? So for such a point z, there are two possibilities. So it flows down. Let it flow down up to a certain time t. And so it could either hit the real line before time t, so that's the first possibility. The second possibility is that it doesn't hit the real line. Yeah? So it is well, that's an obvious dichotomy, like in complex dynamics. So that's the basic dichotomy here. So the ones that fall into the real line before time t, they form a set kt. That's the hull. And the points that stay in the upper half plane, so for which the equation makes sense up to time t, that's the complement. That's a set ht. Can you see this thing down here still? Yeah. So that's a basic fact that the time t map gt is a conformal map from this good set. So here the red set is all the points that stay in the upper half plane up to time t. G sub t is an analytic one-to-one map from this domain ht to the upper half plane h. So that's depicted in this picture. So kt is the green set in that picture here. These are the points that fall into the real line. If they fall into the real line, they actually have to meet the singularity. So they fall into the real line before time t. And then the conformal map, what it does in this picture, kt is just a slit. So the conformal map, it just takes the slit and it kind of opens it up. Yeah? So this slit will be open up to form an interval in the real line. So that's the definition of kt. So now what you could do, eventually, of course, we want to take for xi, continuous function, we want to take Brown in motion, but it's instructive first to look at the case of just a continuous function, just what I call the deterministic case. Yeah. So just take a continuous function, deterministic case, a continuous function xi from the real line to itself, and you can ask yourself, what is the set kt? What does it look like? So there is a theorem of Don Marshall and myself, which basically says that if xi is well behaved, then the situation is nice. If xi is lib1/2 with a small constant, then the set kt is a simple arc, as in the picture before. It's a Jordan arc, a curve with no loops. It doesn't hit the real line. So it's a curve that starts at 0 and just moves up. So that's the good news. There is, yeah, a very good point. There is a constant C0, so that whenever you have a Hölder continuous function with exponent 1/2, factor at most C0, you get an arc, a simple arc. So that's a nice thing. The bad news is that this is sharp in a sense. So if the constant is allowed to be larger, then this is far from true. It could still be an arc, but it's also, there is an example with the lib1/2 function for which you get a topologically very bad object. So it's not even locally connected, so you can't draw a curve through it. It's terrible. Everything can happen past a certain threshold. So it kind of answers. That was a, well, I guess, never mind. So it's kind of sharp, but it's not useful for us here because we want to use for psi Brownian motion, and Brownian motion is not a lib 1/2 function. By law of iterated logarithm, it's just not lib 1/2. So this doesn't give us anything for Brownian motion, and so means we cannot use deterministic results. I won't give any proofs here, so. But just to see how you can attack such a deterministic case, well, if you have a slit, the conformal map opens up the slit, makes 2 halves out of it. So take a point on that slit. It corresponds to 2 points after the conformal map. And so there is a homeomorphism from this 1/2 to the other one, which tells you how to identify them, how to form the slit. And now you're on a real line, so you have a differential equation on the real line. That's kind of easier to work with. So you can analyze the Loewner equation on the real line to show that this homeomorphism is what is called quasi-symmetric. And then there is a lot of machinery that allows you to prove that it's nice. So I won't say anything about this. So, but now I want to turn to SLE. So it's the same equation. You just stick in a continuous function. Now we take Brownian motion as a continuous function. We take a certain time change. So we have this parameter k here. So we take Brownian motion b of kt. That's my continuous function. It's a random continuous function. And you wonder the same question. What is a set kt? What does it look like? So the one result mentioned by Odette already. So these are now all joint results with Odette. So the first theorem here is that if kappa is not equal to 8, at 8 it should still be true, but then we don't know how to prove it. This set SLEK is still nice. Yes? So the situation that I mentioned before cannot happen. It cannot be topologically bad. It is a nice set that you can run a curve through, so it is generated by path. I'll show, instead of giving a rigorous, so here is a green is always, don't read it. Green is a technical statement. So I'll explain on the picture what I mean by that, okay? So, but technically what it means, well, one implication, once you have that it is topologically nice, that it is a path, then it means if you take the inverse of the conformal map, so GT mapped this domain HT to the upper half plane. If you take the inverse, FT, which maps upper half plane to that good set, this is continuous in the closure of the upper half plane. So conformal maps in the upper half plane, they usually tend to be wild on the boundary. They're not continuous at all. But in this case, it turns out they're continuous up to the real line. And if they're continuous on the real line, then you can stick the singularity into the function, and that will, the singularity sits on the real line, and that will actually parameterize the trace. So now let me make it rigorous in the picture. Oh, that already explains what it means, and here is another, well, the same way, but another picture how to look at it. What does it mean to be generated by a path? So I have this compact set, this hull K sub t, the green set here. I want to explain what it means that it is generated by a path. So I don't really want to start with the set kt. I want to rather start with a path. So suppose you have a continuous path gamma here. So it's a curve just in the upper half plane. And so this is the curve here. So it does something like this. And I take only part of the trace. So here I take only the trace up to, say, time t equals 1. Here I take more up to time t equals 2, up to time t equals 3. So this is the picture we get. Then the outer domain would be this one here, the red set. That's what I called HT before. The hull would be this green set. All you do is you just fill in these bubbles here. And you see basically this is if you started with a hull, that would be the path that generates this hull. And conversely, you could say, well, if I had started with that curve, then I could run the Loewner equation. The Loewner equation runs both ways. You stick in a continuous function, you get out a path, if it's nice. But you can also stick in a path first and get out a continuous function on the real line here. So view it this way. You started with a path, run the Loewner equation to get a continuous function on the real line, and then this would be the hull of that process. Here I've just drawn the outer boundary. That's another important set associated with it here. So just the outer boundary of the hull. You see the outer boundary is not quite the same as a path because it forgets about these inner portions. Okay, so instead of saying anything about the proof of the continuity result, I want to mention at least another continuity result that is quite useful, at least technically, and it's nice for complex analysts at least. So This is about the continuity property, not of the map GT, which mapped the complement of the hull to the half plane, but the inverse. So take the inverse, which is a conformal map from the half plane to that nice set. And the statement is that this map is Hölder continuous. So almost surely it is Hölder continuous in the upper half plane. So it's a conformal map of the upper half plane, and remember they usually don't extend to the real line here, but if they're Hölder continuous in the upper half plane, then they obviously extend to the real line, so they're nice maps. And if kappa is not equal to 4, then it's Hölder continuous. Here it's not a technical, it's not that our proof doesn't work, but it's not Hölder continuous anymore when kappa is equal to 4, so that's a slightly different behavior. So the green stuff again tells you what is Hölder continuous, but it says Hölder continuity is you take the difference of the image of 2 points, z prime, and it should be like z minus z prime to some exponent. This exponent depends only on kappa, so for every kappa you have a Hölder exponent. The proof also, don't even look at it too much, but I mean, analysts, of course, for analysts, it's kind of obvious what to do. If you want to prove Hölder continuity, you estimate the derivative. And if the derivative doesn't grow to infinity too fast as you go towards the boundary, then you can just integrate the derivative and get an estimate for the displacement. So that's very standard. You don't quite integrate over a straight line. You have to integrate over geodesic. So this thing just boils down to proving something about the derivative, just controlling the derivative. So if you can show that the derivative doesn't grow too fast, so you have an estimate that the probability grows like this, well, with a control on the probability, then you can easily, well, you don't need to control the derivative at every point, only at these dots here in such a picture. And then you can sum up over all of them and get that, well, this never happens. It happens only finitely often. So the problem in getting any handle on the regularity of this map is just in estimating probabilities for derivatives. So expectations for the derivative is what you really want to control. So control the expectation of some moments of the derivative, and you are in business. I'm too fast, right?
What process is SLE 4 supposed to correspond to?
Oh, that mentioned that interpretation. I think that's just Rick's, right?
Oh,
with these domino tilings and take 2, yeah.
Okay.
It also corresponds to the box model with still control.
Oh, okay. No, I mean, I was just wondering what is going on there. Right, okay, yeah, now I know. I mean, now that you told me that, now right.
So here I've motivated that it's important to control the derivative, but this is more technical, so I don't want to say much about it. I just want to put up one slide. Don't even read it. I mean, just meant to indicate that there are theorems that we can prove here. So, but I think one of the key issues here is that this Loewner, the conformal, the GT, is actually, at least when you translated it by the singularity, by this Brownian motion, it is an Ito diffusion here. So you see the derivative of the GT is just 2 over GT minus psi, the d psi is d psi. So you have an Ito diffusion, so you can use stochastic calculus. So what you can do in order to control such a moment is basically you use Ito's formula, you get a second order PDE, and you try to solve it, so you get estimates or even formulas for the derivatives. And using those estimates, then you do what I said before. You just integrate the derivatives, so you get regularity of the conformal maps. I mean, I don't want to say more about it. Is it okay? Well, now you wonder how many slides might I have if I rush through them. I think it's not so many more. But the more important thing, what I want to mention here is actually there are different phases. So now once we know that this K sub t, this hull, is topologically nice, that it is generated by a curve, you can ask what kind of curve is it? And that depends on your parameter kappa. So when kappa is between 0 and 4, 0 is the only case where you can actually calculate. Then it's just a straight line segment. But between 0 and 4, it is almost surely it is a simple path. So it's a path in the upper half plane which starts at, say, 0 if you normalize Brownian motion at 0 to be 0. So it's a simple path. It doesn't have any loops. And it's a simple path. Well, one can also show that it goes to infinity a bit. it's a simple path. It doesn't hit back on the real line either, so it's a simple path in the upper half plane. Okay. Here I should like to mention that this is extremely influential. This paper of Odet's, the Israel Journal paper, that started the whole thing. He already conjectured this, and he already knew that for kappa greater than 4, you cannot have simple path. And he also proved that if you can show that loop erased random walk has a conformally invariant scaling limit, this is what he mentioned, then you would get this for free for kappa equals 2. So he showed if loop erased random walk has a scaling limit that is conformally invariant, it would be SLE2. And he also proved independently, he mentioned that any subsequential scaling limit produces simple curve. There will be no loops in the limit. So this is a special result of the still to be proved result of the existence of scaling limit of loop erased random walk. But it's in general, this is what we get. So for kappa, then when you increase kappa, so between 4 and 8, then it's still a path. So I've drawn this path over here, but now it starts to hit back on the real line, and it hits back on itself, and it grows those bubbles. So this is what we call swallowing. So there are points in the K sub t would be the filled-in set with all these bubbles filled in. So if you pick any point in the upper half plane with probability 1, it will be in KT eventually, so KT swallows it, but it will not be on the trace itself, not be on the path. So the path has to kind of go around it and swallows it. That happens with probability 1. So this would happen, for instance, for the SLE6, so for the percolation cluster limit. And then finally, when you keep increasing kappa, so for kappa being 8 or larger, then the thing gets a bit wilder. So then it doesn't have these bubbles anymore. Then it's actually piano curves. So I don't know how to draw them. This is how I drew them. So you don't have the swallowing anymore. Every point is eventually in the trace itself. So well, I don't want to say anything about. Pardon? When kappa is infinity. Oh, that's a good question. Now you take it's still a piano curve. So.
No more transitions after 8?
Oh. Well, if you have a suggestion, what could...
They are all different with different kappas above 8?
Pardon?
They are all different with different kappas above 8?
Oh, yeah, I'll say something about the outer boundary later. We have the Hausdorff dimension for, I think it's your conjecture, it makes sense here. So I'll say something. They're different for different kappas. Yeah. Wait a couple of slides. Okay. Well, the only thing I want to mention here is just one thing one way to control. Take a point in the upper half plane, look at the distance to the trace. So d of z is a distance of the point to the trace. Then, well, if that point would be on the trace, the distance would be 0. And if it's not on the trace, then it would be just some random variable. So it's kind of natural to control this distance here. And for complex analysts know that under conformal map, well, the distance to the boundary just behaves it's distorted by the derivative of the conformal map at that point. So from this, you can at least guess that somehow what you want to do is, again, you want to control the derivative of the conformal map. Now it's a little bit different. Now you have to stop it at a certain time. But then there are estimates for the moments, again, of the distance. And they tell you exactly what happens in these different ranges. So I guess we don't really want to work through this. So I think what might be interesting is now to look at the trace and look actually at its dimension. Maybe I should cover up all this stuff here. So in Wendelin-Werner's notation from the introductory talk, this is what we prove. The dimension is 1 plus kappa over 8, but it needs to be interpreted here. So, in quotation marks. So what we want to do is we take this trace here. Well, why don't I show everything? This is what I mean. I'm not a transparency person, So you take this whole trace. Gamma is this SLE kappa trace, so you let it run for all time, so you get this kind of infinite path in the plane. for technical reason, you look only at a certain window. So take some open set that stays away from the real line here that is bounded and intersect the trace with it like in here. And just count the number of disks of size epsilon that you need in order to cover that set. So then we have an estimate for the expected number of disks needed to cover. And this expected number of disks needed to cover grows like, well, it's 1 over epsilon to the power 1 plus kappa over 8, basically. Then there is some, for the upper bound, there is some logarithmic term here. And for the lower bound, there is, well, such a logarithmic term. This one probably shouldn't be there, but I mean, it's in the proof, so at this point. So the upper bound is true for every epsilon. Yeah. The lower bound is true only on a sequence of epsilons that goes to 0. But this comes off from the proof. I mean, the final result of somebody else probably will be much finer. But this is roughly what is happening here. But so the expected number of disks grows like 1 over epsilon to the 1 plus kappa over 8. And a simple, very simple immediate consequence from that is that the Hausdorff dimension of this path, so now take this SLE kappa path, then the Hausdorff dimension of that path is bounded above by 1 plus kappa over 8, almost surely. So almost every point, path has dimension 1 plus kappa over 8. And, well, of course, the lower bound wants to be true. I mean, it is true, I guess, but we don't know how to prove it at this point. Any questions? Yeah, so kappa equals 6. Let's do an exercise. For kappa equals 6, so you get 1 plus 6 over 8.
Right, I get that, but my question was... you did the exercise. But on that claims that we have equality for calculation.
Yeah, so why do we get, what is it here, 7/8 and not 4/3? 7/4. I'm not exactly. What is the difference? Well, the difference is that this is a whole trace together with all the bubbles. Yeah? So now we want to remove all the inner stuff and we want to look at the outer boundary. So the outer boundary of the SLE6 is the same as the Brownian frontier. So what we want to do, well, maybe I should use this other projector. Yeah, I still have. Come back to this one picture here from the beginning. So, whoops, I guess, like this. So this is not exactly how the SLE6 looks like, but I mean, qualitatively you have these bubbles here. Yeah? So you have such a path that doubles back on itself, and what I just, so that would be the SLE6 path, say. And what we've just calculated is how many disks do I need to cover the whole trace here. Yeah? And that gives you the dimension here. But now if you want to look at the outer boundary, so for you forget about all this inner stuff here, so you get the smaller, the subset here, then you expect it's a smaller set, so it should have a smaller dimension, and that's the last slide, well, almost, which is about the dimension of the outer boundary. So now, in Wendelin's notation from the introductory talk, it would just be dimension is 1 plus 2 over kappa, but with an obvious interpretation. So now we might want to restrict to the case that kappa is greater than or equal to 4, because before 4 we have these simple arcs, and for a simple arc the outer boundary is the same as the whole set. So there we still have the 1 plus kappa over 8, but past that we get the 1 plus 2 over kappa. And again, we intersect with some set, so now we just take an upper half and we slightly slide it up, so we take all the y's bigger than h, and then we have the well, now we don't have expectation result anymore. Now it's just a probability. So almost surely the number of disks needed to cover grows at most like 1 over epsilon plus, in the exponent 1 plus 2 over kappa. So 1 plus 2 over kappa is the right exponent for the outer boundary. So this is for kappa bigger than 4 is smaller. And now if you take kappa equals 6, you get the 4/3. So the lower bound is true for the expectations, and again only on a sequence of epsilons that goes to 0. Yeah? So at the same exponent, now you just have a little of 1 here. And you have the same, well, obvious corollary here, the Hausdorff dimension of the outer boundary. The 1 here indicates you have to stop this thing at some, For this one, you don't need to. For the dimension, you don't need to stop it. But here, for the number of covering this, you have to stop it at some time. So let's take the trace only up to time 1. Anyway, the dimension is bounded by 1 plus 2 over kappa, almost surely. And now I'm really kind of out of time here. So I don't want to. This just indicates that there is a proof. And for the what you can do here is actually this is one way to prove that is to take a Whitney decomposition of the complement. So you fill the complement up with squares so that the squares are comparable in size to the distance to the boundary. And then you would like to look at the diameters of those squares, and you would like to look at the convergence exponent of this. Well, how many squares of a given size do you have? You like to count those. Now, the number of squares of a given size, that's related to the number of disks of radius epsilon you need to cover the outer boundary, but it's not quite comparable. So the number of Whitney square needed is bounded above by the number of, is a lower bound for the number of disks you need to cover. But in general, it's not the inverse inequality is not true. So one of the technical things here that is kind of lucky is that the SLE boundary is so nice. It's a Hölder domain. I mentioned before that the conformal map is Hölder continuous, and then there is a nice result of Nick Makarov's that says, well, it's also Pommering first, that in this case you can actually find the dimension of the boundary of a domain just by looking at the Whitney cubes. So you just have to look at this, and this boils then down again to looking at derivative estimates for the derivative of the conformal map. So kind of the estimates that I mentioned before. So nobody stood up, so before the chairman stands up, I quickly put up this last slide here, just the summary slide. I guess. So what was the most important thing, what I mentioned here? The SLE trace itself, it is a trace. That was I mean, it really is it is a curve, and you have these different phases. You have a simple path between 0 and 4. You have the swallowing path, which forms bubbles between 4 and 8, and you have a piano path above 8. And then these dimension estimates. The dimension of the trace is 1 plus kappa over 8. The outer boundary is 1 plus kappa over 8 up to 4, and then after 4 it is 1 plus 2 over kappa. That also then answers the question. So for different kappas you get different dimensions. So even if kappa is past 8, they must look different. Wow. Yeah, it is. What?
But you dimension u plus 2. At kappa equals 8, you have 2.
Oh. This one here is true only up to kappa equals 8. You're right. I mean, then the piano path has always dimension equal to 2. So this I didn't write down, that the trace after kappa equals 8, the trace cannot increase its dimension anymore. But pardon? Yeah. Thanks. That's why I left. Yeah. So here are the problems that we haven't answered that are certainly interesting problems. Is SLE8, we haven't been able to prove that it is a path, but it should be a path, so that needs a proof. Then also this continuity of the conformal map. So we prove it's Hölder continuous for kappa different from 4. So what happens at kappa equals 4? There still should be some kind of modulus of continuity, some logarithmic stuff. So that would be good to have. And then, of course, to make these inequalities, make them equalities. So thanks for your attention. Ask with that. Oh.
Did you explain equality on your stance?
Well, when for SLE6 we know it's equal to percolation cluster, it's equal to the boundary of Brownian motion, and then we know the Hausdorff dimension by other things. So Greg Lawler had a paper showing an exponent is equal to the, you can get from the exponent the Hausdorff dimension. Rendeling where we computed the exponent. So it's an entirely different proof. It's valid for
I'm trying to understand these distinctions between paths. You speak about a simple path, and you have the swallowing path, which you explained. But now in the problems, you say you question whether SLE8
Oh, well, you remember, yeah, so this is what I tried to, I didn't make that very clear, I guess. I mean, for all kappa different from 8, we can prove that it is actually, it's a continuous, so you have a function gamma of t, which maps the real line, say the time interval, into the upper half plane. Yeah, it starts at 0. And for all kappa different from 0, kappa different from 8, we know that this is a continuous, there is almost a continuous function which generates that SLE. For kappa equals 8, our proof doesn't work. So you're right, I should have been a bit more careful when I spoke about the SLE. I mean, this is a question. Yeah. Yeah, so it should be, for every kappa, it should be, it is a path, I guess. Yeah, but for kappa equals 8, we can't prove it.
Could you show us the picture of the example where it is not a path?
Yeah, there is, but this is a deterministic example. So if you take, in the upper half plane, so you take like a logarithmic spiral which doesn't shrink down to a point. So if you take such a curve which circles around the disk and accumulates towards the disk, yeah, and then it spirals out again. Yeah. In this case, so this is, I mean, kind of a curve. So at least if you cut off this curve at different times here, so you also get such an increasing or decreasing sequence of compact sets. So you can call these sets for various parts of this. This gives you k sub t's. So that gives you the Loewner equation. So that gives you a continuous function psi of t. So what I'm saying, there is a continuous function psi of t, which if you put it into the Loewner equation, it produces such a weird thing. And so in this case, well, the kt is not generated by a continuous curve. Because, I mean, this one looks pretty continuous up to the discontinuity at the circle. But you can put those things everywhere.
Around infinitely many times up to some finite.
No, it just goes around infinitely many times.
Up to some finite t, and it comes back out.
Exactly, and then it comes back out. And you could put those everywhere. You can make them dense. This is not the worst topological continuum here, but this is what can easily happen already with a lib 1/2 function. Yeah, so that's the example that I mentioned in the deterministic case. So there's a function that, in a sense, is smoother than Brownian motion, which produces this already. Oh, it's just a function like squared. Actually, this I always wanted to. I think I'm trying to find a good graduate student who will prove this. You can take for psi of t. It's an analytic. You can even take a real analytic function. Almost square root of t with a large constant. Yeah, we'll already almost do it. There might be a slide also, maybe let's throw in something that I don't know yet, a sine t or so. Yeah? But a very nice function that you can write down explicitly. It will just have one singularity that corresponds to this thing. It's a very, very smooth function. Loewner equation is hard to understand. This problem, what functions generate simple arcs, that has been around for, the counterexample was given in the 50s, and since then there wasn't really much progress, I guess. So it's unfortunate, but
ask further questions in private.